We're finishing the semester with a local speaker, Kravitz, who will tell us about corners with polynomial cycles.
Okay, thanks, Elon, for the introduction and the invitation, and thank you all for coming, especially those of you who have already heard this talk. So I'll be talking about joint work with Borys, Kuca, and James Leng on corners with polynomial side length. And this is a project in higher order Fourier analysis, which I know has a reputation for being very scary. So I've tried to make this talk accessible and highlight standard tools and how they apply to our problem. And please interrupt me if you have any questions or things are unclear. So background, what is this field of arithmetic Ramsey theory? In a nutshell, it's asking what kinds of configurations you can always guarantee to find in sufficiently large sets of positive density. And the first result in this direction was due to Roth from 1953. And he says that every 3 AP-free subset of the integers 1 through n must have size little o of n. And then Simonyi famously generalized this a couple decades later, and he says for every k, a k AP-free subset of 1 through n must have size again little o of n. Yeah.
Sorry, what's AP-free?
AP for me stands for arithmetic progression. So I say that a set is 3 AP-free, for instance, if it does not contain a 3-term arithmetic progression with non-zero difference. So I'm looking for points x plus y, x plus 2y, where y is non-zero. And here
you could state it positively, that if you have positive density, you can find them.
Yeah, it's equivalent. It's the contrapositive. Yeah, so if I give you 1% of the points 1 through n, and n is large enough, then you can always find x and y such that x, x plus y, and x plus 2y are all in the set. Does that help? Okay, good. Please continue to interrupt. Right, so Simonyi says you can do this for k-term progressions for any k. In a somewhat different direction, Furstenberg and Sarkozy independently showed that if you have a subset of 1 through n that does not contain 2 elements differing by a perfect square, then the set has size little o of n. So here you're looking at just a 2-point configuration, but it's sort of nonlinear. There's some polynomial behavior in the difference. And then the one theorem to rule them all is due to Bergelsen and Liebman from 1996. And their theorem looks a little bit more technical, but it generalizes all of these. So the configuration that you're looking for is this thing down here. So you pick a base point x, and then you take shifts in the direction p1 of y, v1, p2 of y, v2, and so on, where the pj's are polynomials, let's say polynomials with integer coefficients, and the vj's are just vectors. So in the one-dimensional case, let's say Roth's theorem, your polynomials are just p1 of y equals y and p2 of y equals 2y. And for Furstenberg-Sarkozy, your p of y is just y squared, and there are no vectors involved. So there's also this technical condition that we want all of the pj's to pass through the origin, and this avoids sort of trivial obstructions. So for instance, you can never have pj equal to the constant 1. You can't guarantee finding a configuration x, x plus 1 in a set because you can just take all the even numbers. So this avoids local obstructions. Okay, so this is the one theorem to rule them all.
That's kind of important because I don't think there's a density version of any kind of theorem which, say in the number theoretic, you can build in local obstructions, and we do that all the time. But I don't think there's a density, and for good reason, there's no density theorems which allow you to solve inhomogeneous equations.
Yeah, that's probably. I mean, if Vitali were here, he would say that there's always a density version of everything, but I don't know he's a practice.
No, but I think there are things of Terry and Tammy and things like that. I think there are some.
No, they lie, they're generalizations. No, for primes, there are many theorems, but I'm talking about for pure density.
Yeah, I'm not sure how we.
You just gave a local obstruction even odd.
Yeah, so it's not clear how to
carry that through all the proof,
Yeah, so this is really, so in this density version as opposed to analogous coloring versions, as Peter's saying, it's really important we have this local obstruction, or that we don't have this local obstruction. Yeah, it's important to include this bit about the local obstruction. Good, okay, so this is the theorem, and let's talk about bounds for this. So the proof of the Bergelsen-Liebman theorem is ergodic, and so it gives literally no bounds for what this little o of n to the d is. It uses ergodic theory, it uses compactness, even in reformulating the problem, there's no hope. So even for particular instances like what I highlighted on the last slide, obtaining quantitative bounds is a difficult and interesting question. So here's roughly what's known. So starting with the examples from the last slide, you can talk about 3-term progressions. The current world record is due to Kelly and Mecca from 2 years ago. And James and Ashwin and Matab recently got some new bounds for k-term progressions. And in terms of this problem about sets avoiding square differences, early work was due to Pinsteiger and Simonyi, and the world record here is due to Bloom and Maynard from a few years ago.
That was just improved by Green and Simon.
Actually, yeah, since I made the slides, this was improved. Thank you. Yeah, so in a somewhat different direction, if you restrict yourself to one-dimensional polynomial configurations, Peluse and Prendeville handled the case where the polynomial shifts have distinct degrees. And then in a sort of different direction, Prendeville, I guess a few years earlier, handled the case of arithmetic progressions in the integers with perfect power difference. So this is where your polynomials are z to the d, 2z to the d, 3z to the d, and these are homogeneous. So this is sort of the opposite of this Peluse and Prendeville regime. And then is sort of a variation of this. Peluse and Sawhney got quantitative bounds for 3-term arithmetic progressions with common difference y squared minus 1. So this has a sort of different flavor from this Sean-Prendeville result because y squared minus 1 is not homogeneous. But it's more difficult than this old result of Peluse and Prendeville because the polynomials y squared minus 1 and 2 times y squared minus 1 have the same degree. And then the only result previously that was genuinely multidimensional was this result of Shkredov on corners. So a corner is a 2-dimensional configuration, which consists of 3 points like this, and these 2 side lengths are the same. Okay, so this is basically more or less what was known in the integers. And I should mention that there are also
What kind of quantification, for instance, for
which
Shkredov's result, what kind of
quantitative bounds.
quantitative bound?
Yeah, I'll talk about this. So if you look at subsets of bracket n squared, you can find a corner as long as your subset has size at least n squared over log n to the 1 over 74. Yeah, which is not bad actually by the standards of the field. Yeah, so somewhat more is known in finite field settings, which is sort of easier for a variety of reasons. One is that polynomials have dense image, but I won't say too much more about this. So this brings us to our contribution, which is that we obtain quantitative bounds for a new configuration, namely the polynomial corner configuration. So the polynomial corner configuration is exactly what it sounds like. I want to take a triple of points, x comma y, x plus p of z comma y, x comma y plus p of z. So this is a corner where you demand additionally that the side length is in the image of some polynomial. And for technical reasons, which I'll return to in a bit, we require our polynomial p to have a simple integer root. And under this assumption, we can say, well, if your set in bracket n squared does not contain one of these polynomial corner configurations, then your set has size at most this thing, n squared over triple log n to the 1 over 74.
What is that? That's necessary, the simple integer?
So we use it comes up several times in our proofs. Morally speaking, it shouldn't be necessary. It's the same type of thing that came up in Sarah's paper with Ashwin and Matab, where they did these 3 APs with common difference y squared minus 1. So this has a simple integer root, and sort of the same obstruction that they have is appearing in our setting.
So if you do y squared minus 2, there would be issues.
I think the proof wouldn't work.
So it's a serious assumption.
I think it's believed that there should be a way around it, but I don't know how to do it. I don't know, Sarah, do you have something to add here?
Well, if the like if the actual density statement is true, like if you're just willing to suffer enough, like
Yeah.
like running the Shkredov argument like relative to pseudorandom sets.
Yeah, but fine, okay. The proof strategy that I'm going to present seems like it faces some serious obstructions. Yeah, there is this other route that you're mentioning.
Like that, I think, like it's just like the will to do it is what's needed. There's no actual like obstructions to doing this.
Yeah, so maybe what I should say is there are obstructions to our proof strategy, but there are these other strategies you could try that maybe you go through. And I can point out, I will point out where we use this simple integer root assumption. Okay, so this is our configuration. It looks like this. We get quantitative bounds for sets avoiding it. So when I gave this talk as a practice talk, I was asked, why do you care about this configuration? So I owe you a few explanations. The first is just that it's a common generalization of this result of Serre and Ashram-Mittal about 3 APs with common difference y squared minus 1. And obviously it also generalizes Shkredov's corners theorem because we get corners with even more constraints. And the reason it generalizes this result about 3 APs with common difference y squared minus 1 is that in general, if you're able to find a corner, you can project it and you find a 3 AP. So that's the next reason, which is everybody likes 3 APs and corners are just like more difficult versions of 3 APs. The other reason is that this is, along with concurrent work of Peluse, Prendeville, and Shao, the first instance of quantitative bounds for an instance of the Bergelsen-Liebman theorem that's both genuinely multidimensional and genuinely polynomial. So before this, we had Shkredov for something multidimensional, and we had a lot of results in one dimension for polynomial configurations, but here we're able to combine the two. And yeah, there's this concurrent work on the configuration x comma y, x plus z comma y, x comma y plus z squared. So this looks kind of like a corner, but our side lengths are z and z squared. And the fact that those are different side lengths makes the proof strategy look very different. So I would say that our result and this result here really don't have a whole lot in common. And then I guess the last reason why we might be interested in such a thing is because of the techniques that we develop along the way. So any question about the result?
So
That
it's
was me.
not less than P?
So there's an implicit constant here which depends only on P.
Okay, and this doesn't depend on like the degree of the,
No, so I mean, the degree affects the implicit constant, but that's it.
okay, great.
Yeah, I mean, the coefficients of P also go into this constant. Yeah, but in particular, this 1/74 is really 1/74. Okay, so let's talk about the proof strategy and how we might try to prove such a thing. So let's say that D is the degree of P, and I'm going to write down something that doesn't look very useful at first. We can express the number of P polynomial corners by this big expression here. So we take an average over x, y, and z, and we take the indicator function of our set A at the point xy times the indicator function of the set A at the point x plus p of zy times the indicator function evaluated at x, y plus p of z. So this quantity here is 1 if all of the points x, y, x plus p of zy, x, y plus p of z are in our set A and form one of our configurations, and otherwise this is 0. So when we take a sum, this tells us the number of corners, of P polynomial corners. So you can generalize this and say, well, instead of taking indicator functions of a set, you can put in any functions, let's say f0, f1, and f2, and you can define this normalized P polynomial corner counting operator analogously for these 3 functions. So the way you should think of this is you take each triple of points forming a P polynomial corner, and you take the product of the functions f0 and f1 and f2 evaluated at those 3 points. And we really will be using this quite heavily even when the FIs are not just indicator functions of our set. Okay.
Why is Z inside this n to the 1/d? Okay.
Yeah, so I take so my set A is in bracket n squared. And so if Z is bigger than n to the 1/d, then P of Z is bigger than n. And either x or x plus P of Z will lie outside of bracket n, and there's no hope of finding the configuration. Yeah, so I could have taken a sum over all Z, but this is just for normalization. Okay, other questions? Okay. So similarly, for the corner configuration, you can define the normalized counting operator in the same way. And now we just have the points xy, x plus zy, x, y plus z. And the idea is that if you can show that for all choices of f0, f1, and f2, lambda p is very close to lambda corners, then we win. So we can apply Shkredov's theorem, which tells us that lambda corners of indicator function of A 3 times is very big. And then if that's very close to lambda p of 1a, 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 then that's also big, and we found many of our P polynomial corners.
So this log n to the 1/74, that's just coming from.
Almost. I'm going to talk about that in a couple of slides. 2 of the logs are coming from Shkredov. 1 of them is on us. Okay, so this is the idea, but unfortunately this doesn't work. So I'm going to talk now a bit about how you can massage things to try to make this strategy work. So let's talk first about Archimedean obstructions. So if I want to compare my two counting operators, one issue that appears right away is that the image of my polynomial becomes sparser at larger scales. Whereas in my corner counting operator, I'm giving all of the values of z equal weight. So we'll fix this. This turns out to be pretty easy. So we'll introduce a smoothly decaying weight, nu of z, into our corner counting operator. And this gives us a model corner counting operator that looks like this. So it just gives larger z, lower weight. And this nu is very smooth, it's very well behaved. And so we know that this is also very big when you put in the indicator function of a for all the fi's, but because you can still apply Shkredov's result. So this fixes the first problem. The second problem is non-Archimedean, and this is more serious. And so for instance, okay, so the issue is that the image of this polynomial can be biased with respect to small moduli. And the example you should keep in mind is that z squared plus z is always 0 or 2 mod 3. Whereas in our model corner counting operator, we're uniform mod 3. And for this, we use the so-called W trick to pre-sieve the set. So this is a very standard trick. If you're a number theorist, you call this pre-sieving. If you're a combinatorialist, you call this the W trick. And I want to tell you how it works because it's really crucial. So the setup is we take little w to be a slowly growing function of n. For us, it'll be something like log, log, log n. And you let big W be the product of the primes up to little w. And now what we do is we say, okay, let's look at the cosets of wz squared. So we're looking at a grid with side length w. And we're saying by the pigeonhole principle, you can find some coset on which the density of A does not decrease. And we can parameterize this set by the pairs x prime, y prime, such that b1 plus wx prime, b2 plus wy prime is in our original set A. And then the question is, what kind of configuration in the set A prime corresponds to a p polynomial corner in our original set A? So if you do out the algebra, you'll get that this works. So we suppose that p has a simple root at 0, and we consider this auxiliary polynomial p tilde of z, which is p of wz over w. And the key thing about this is that it still has integer coefficients. So p having a simple root at 0 means that it has no constant term, and it has non-zero linear coefficient. So when you plug in w of z into p, all the coefficients are multiples of w, and you can divide out by w, and you still get something with integer coefficients. And if you work out the algebra, p tilde polynomial corner in our set A prime yields us a p polynomial corner in the set A. So it suffices to show that if we can always guarantee finding p tilde polynomial corners, this is good enough to find p polynomial corners in general. Good. And why is this useful? This is useful because p tilde has better divisibility properties than p. So let me write down an example to show you what I mean by this. So let's take our example here, where p of z is equal to z squared plus z, which we saw does not equidistribute mod 3. Then p tilde of z is equal to w squared z squared plus wz over w. This is wz squared plus z, and this is equivalent to z mod w. And in particular, this means that p tilde of z equidistributes modulo all of the small primes. So this fixes our mod 3 problem. And this is where we win. So let's return to the proof strategy. And the punchline is that with these two modifications to fix these Archimedean and non-Archimedean obstructions, our transference strategy will go through. So the statement is that if you have any functions, f0, f1, and f2, which are one bounded on bracket n squared, then lambda p tilde minus lambda model is very small. So I haven't told you how large n has to be in terms of delta. It's something quasi-polynomial in 1 over delta, but sort of qualitatively, this is the type of thing that now becomes true. And then the main theorem immediately follows. Because if you have a set A which has no p polynomial corners, then that has to be small. In other words, if you have a large set, you can find many ordinary corners, and then by the transference theorem, you can find many of our p polynomial corners. So now I can answer the question about the logs and where these come from. So 2 of the logs in the 1 over 74 come from Shkredov's result, and then the third log comes from our transference theorem. So it's in what comes out of this quasi-polynomial mess when you work it out. Okay. So this transference theorem is proven basically by analyzing two different cases. What happens if this thing can be large? So the first case is where lambda p tilde and lambda model are both small. Then their difference is automatically small, there's nothing to show. And the interesting case is where at least one of these is large. And then what we want to show is that if either lambda p tilde or lambda model is large, then our function f0 must look like a function of the form g of x h of y. And if you can do this, you can basically plug this back in for f0 in the expression up there. You Fourier expand everything out, you do some manipulations, and then using this smooth decaying weight that we put in and the W trick, you can eventually show by hand that there's cancellation. So this is the overall strategy. And the difficulty, as you might expect, is getting this kind of inverse theorem. So we want to understand when is it possible for lambda p tilde and lambda model to be large? Okay, and in order to make this precise, I need to say a little bit about box norms. This is the worst slide in the talk because people who already know about box norms will be bored and people who don't know won't be able to digest it, but I'm going to put the definitions here in general and then zoom in on the case that we need. The setting is that G is some abelian group, Z squared, maybe FP squared. And the first thing we defined is the multiplicative discrete derivative. We have a function f on our group G, and you have some element h, and we define the multiplicative discrete derivative of f with respect to h to be partial hf, and this has the value of x, which is equal to f of x times the complex conjugate of f of x plus h. And if f is of the form e of g of x, then you can think of this as taking an additive discrete derivative in the phase. And here's the scary definition. Now we take E1 through ES to be finite subsets of G, and we define the box norm of a function f along these boxes, E1 through ES, to be this big quantity here. So we take an average over HI's in the EI's, and then we take a product of all of these discrete derivatives with respect to H1, H2, all the way up to HS of f, and then we take a sum over all choices of x. And it turns out that this is real and non-negative, so you can take this to the S root. So this is a lot to digest, but I want to highlight two special cases. The first case is where G is finite and all of the EJs are the same. And then this gives the Gowers U to the S norm, which you can think of as an average along S-dimensional parallelepipeds. Okay, and the thing I should mention here is that the U2 norm is up to normalization equal to the L4 norm of the Fourier transform. And this is known to control three-term progressions. So if you have a set A and you want to know how many three-term progressions are there compared to, say, a random set with the same density, it's about the same as what you get in a random set of the same density, unless it has a large Fourier coefficient. And this is picked up by this Gowers norm. And if you want the analogous statement for longer progressions, you need these higher degree Gowers norms. And I guess since this is a dynamics seminar, I should mention that these infinite versions of these Gowers norms also appear in ergodic theory as sort of which you can use to define characteristic factors for certain averages. Okay, but I won't say much more about the ergodic stuff. Our favorite norm for this talk is going to be the U1 cross U1 norm. And this is where our group is a product group, G is H times H. And our first box is the x-axis, and our second box is the y-axis. So this U1 cross U1 norm is an average of f along axis parallel boxes. And here is a closer look at this U1 cross U1 norm. It can be written as follows. So it's the sum over x and y and an expectation over hk, where you take these two discrete derivatives in the direction h0 and 0k of your function f. And when you write everything out, you get this. Let me write this here. So here are the vertices of my axis parallel rectangle, and I'm taking a product of f evaluated at these vertices. And the really convenient thing about this U1 cross U1 norm is that it has a convenient inverse theorem. If you know that the U1 cross U1 norm is big, then you can conclude that the function has a very special form. Namely that it correlates with the function of the form g of x h of y. And if you recall from before, this is just the type of conclusion we're hoping to get. So I'd actually like to prove this for you, because it's really easy. So let's take this and let's just write it out. Let's do a change of variables first. So I'll replace h with x prime minus x, and I'll replace k with y prime minus y. And then we can rewrite this. So suppose we have our function f, which has large u1 cross u1 norm. This gives us delta h squared is at most, or yeah, is at most this u1 cross u1 norm. And let's just write this out. We'll have an expectation over x prime, y prime, and a sum over x and y of f of x, y, f of x prime, y, f of x, y prime, f of x prime, y prime. Okay, and now what we'll do is we'll pigeonhole in x prime and y prime. So we find that there's some x prime and y prime such that this guy in absolute value is at least delta h squared. So we can pull this out of the absolute value. This doesn't hurt us. We have sum over x and y, f of x, y, f of x prime, y bar, f of x, y prime bar. And the thing to note is that this is a function only of x, and this is a function only of y. So there's really nothing happening here. And you can do the same thing in the integer setting, where now instead of taking the whole x and y axes, you just take intervals, and the proof of the inverse theorem is basically the same. So with this in hand, we can say the main technical result, which is that we have u1 cross u1 control for the operator lambda p tilde. Okay, and what do I mean by this? As I mentioned, to show our transference theorem, it suffices to show that if lambda model or lambda p tilde is large, then f0 correlates with one of these functions of the form g of x, h of y. And to get this conclusion, it's enough to show that it has large u1 cross u1 box norm. And this is what we will show. The first half of this is routine. If you just apply Cauchy-Schwarz, I think twice, to the model counting operator, you'll get that largeness of that implies the largest of this u1 cross u1 box norm for f0. But for the lambda p tilde operator, it's more difficult. And we show that if n is large enough and you have one bounded functions f0, f1, and f2, such that this lambda p tilde is large, then you do have largeness of this u1 cross u1 box norm on f0 with this quasi-polynomial bound. Don't pay much attention to the quantitative bounds, it's just what you get. And the proof of this theorem, again, breaks down into two steps, and I'll spend the rest of the talk outlining how this works. I should also mention, at this point, you can completely forget about the W trick and the smoothly decaying weight that we put in the model operator. The W trick makes everything much messier, but it doesn't fundamentally change this argument.
One reason that I was eager to hear this talk was because we were talking in my office with the word concatenation, which just arose now.
Yes.
Can you explain that?
Yes, that's the next slide.
And that's what they were using?
That's what they're using.
Concatenation argument from this paper.
Yes.
Yeah, good.
Yes, I won't give the full argument, but I'll give a flavor, a taste of it.
Okay, excellent.
Yeah, so the first step is, as Peter said, use pet induction and quantitative concatenation to obtain the same conclusion of this theorem, but with the u1 cross u1 norm replaced by a ut, or sorry, yeah, a ut.
What is pet induction?
I'm gonna do that on the next slide.
Okay.
This is an overview of the two steps of the proof, and I'll explain all of the words.
While you're doing it, also point out to us where you need this strange condition about simple integer.
Yeah, so it appears in two places.
You already use it for the W trick or not?
So we use it to get the W trick started, but we use it,
Yeah, you see, that's kind of building this homogeneity there.
where is it? We use it here. So we plug in this, after we do our Fourier expansion, you end up having to show some, yeah, you end up, no, we use the simpleness of the root.
Simple.
Here, because we end up having to show the Fourier uniformity of some weight. And it turns out that the polynomial appears somewhere in the definition of the weight, and we need this in order to show equal distribution mod small primes. And the second place appears at the very end of the argument in step 2 here. Step 1 does not use simple integer root or anything. So step 1 is we obtain the conclusion of the theorem with this degree 2 box norm replaced by a box norm of larger degree. So instead of differentiating once in the horizontal direction and once in the vertical direction, you take t derivatives in the horizontal direction and t in the vertical direction, and this is something you can get. And the second step is we use something called degree lowering to reduce t down to 1, which is the conclusion of the theorem. And I should say that this proof framework is not new. Both steps of this have been done before, but there's something new in how we execute them. This pet induction and quantitative concatenation is pretty well known. And in any particular case of a configuration, people have been able to do it, but we do it in full generality because it turns out that our polynomial corner configuration is sufficiently complicated. Handling that is as hard as handling the general case. So this is not anything which was fundamentally unknown before, but we actually did all the work and figured out the details. And then this degree lowering also is something which has been done before. Sarah basically pioneered it. And in the past, it's been done with Gowers norms. And this is the first case where we do degree lowering using box norms instead, which presents some sort of different technical difficulties. Okay, so in the rest of the talk, I'll give sort of a sketch of how each of these two steps works. And we'll start with pet and concatenation, as Peter wanted. So the way I'm going to do this is I'm first going to go through an example, and I will hopefully do all the calculations on the board. And then I'll explain how it generalizes. And the example that I want to do is the 2-point configuration x comma x plus y squared. So this is 2 points differing by a perfect square. And we want to see if we can get Fourier control on this. So U2 control. And I should say that this pet and quantitative concatenation is not the best way to handle this configuration. You should just do the circle method immediately, but this illustrates a lot of the ideas. And okay, so let's do this. So the associated counting operator is this lambda, which is a sum over x of an expectation over y of f0 of x, f1 of x plus y squared. And we're going to assume that this is large for some one-bounded functions, f0 and f1, and we're going to see what we can get. The first step is we're going to do pet induction, which consists of using the Cauchy-Schwarz inequality over and over again to isolate the argument f0 and then take discrete derivatives to make the y squared vanish. So let me show you how this works. Okay, so we start with this. And the first thing I'm going to do is I'm going to, I'll write this out. The first thing I'm going to do is I'm going to do a change of variables, and I'm going to shift x by y squared so that the second argument does not depend on y. So let's shift x to x minus y squared. And now I'm going to Cauchy-Schwarz. So this is a sum over x of this guy times this guy. What do you get? You get delta squared, n squared is at most a sum over x, f1 of x squared times a sum over x of f0 of x minus y squared squared. Sorry, I'm missing a term. Okay, and let's look at this. So I assume that the functions f0 and f1 are one-bounded pointwise. So this f1 of x squared is at most 1. And f1 is supported on bracket n. So here I'm adding up n things of size at most 1. So this whole thing is at most n. And I can divide through both sides by n. and let's see what we get. So when I write this out, I can expand out the square, and I'll get an expectation over y and y prime. And you can replace y prime, the second copy, with just y plus h, where h is some new variable. So I'll fudge this a little bit here. Okay, and now we play the same game. So what I'll do here is I'll do another change of variables so that the argument of this second copy of f0 doesn't depend on, y and h. It doesn't depend on y. I'll move it out front and then I'll Cauchy-Schwarz. So let's change x to, let's shift this by y squared plus 2hy. What we'll get is that delta squared n is at most a sum over x, the expectation over h of f0 of x minus h squared times an expectation over y of f0 of x plus y squared minus 2hy. And now we'll Cauchy-Schwarz again. And again, this term doesn't cost us anything. So we get delta to the fourth n is at most this sum over x, an expectation over h. So now I'm going to have this y variable, and I can again replace the second copy of this from the Cauchy-Schwarz with a y plus k. So h k y of size n to the 1/2. And what I'll get here is f0 of x plus y squared minus 2hy times f0 of, maybe I dropped something. This looks right. X plus, let me make sure I did this right. Yeah, y plus k squared minus 2hy plus k. And now we're going to do another shift. So we're going to shift everything by y squared minus 2hy. So x, and send this to x plus x minus y squared plus 2hy. And we'll get that delta to the fourth n is at most this sum over x, this expectation over h, k, and y of f0 of x, f0 of x minus 2hk bar. And the y has disappeared, so we don't need it. And this thing here is precisely an average of box norms. So hopefully I've written it here. Okay, I didn't write it. So let me move over here. So this thing from the previous board was delta to the fourth n was at most an expectation.
Does PET stand for?
Doesn't stand for anything anymore. It used to stand for polynomial exhaustion technique or polynomial ergodic theory, but now it's just an acronym. Or it's not an acronym. So I'm going to write this out in a sort of different way. Okay, so if I just take the thing there and I rearrange, I get that this is the largest of an average of box norms, where our boxes are now arithmetic progressions with common difference 2h. So this is a start, but it's not what we want because we want a single box norm, not an average of box norms. And this is where the quantitative concatenation comes in. And we want to try to replace this expression 2hk here with something with better equidistribution properties. So let me let me write down what this really means. So if this quantity 2hk is well distributed, then something nice happens. So if the number of pairs hk such that 2hk is equal to t is bounded by a constant for all t in bracket n, then by the triangle inequality, the previous equation, let me call this star. And what do we get from star? Star gives this delta to the fourth n squared is less than expectation over t of size n of the sum over x of f0 of x, f0 of x plus t bar. Okay, so this is looking a little bit better. I've replaced this expression. Oh, there's a 2 here. No, there's not a 2. So I've replaced this funny looking expression hk with a single new variable t. And then what we'll do is we'll Cauchy-Schwarz one more time to get rid of the absolute value. And we have this expectation over t. Then we have a sum over x and y of f0 of x, f0 of x plus t squared. And this is equal to your degree 2 box norm when you expand this out. So this gives us okay, so if we have this anti-concentration result, then we can just we use the triangle inequality and we do a couple of extra Cauchy-Schwarzes and we get the largeness of this U2 norm. Unfortunately, this is not the case. We do not have this anti-concentration. So what we do is we start from equation start and we apply Cauchy-Schwarz again and try to hope that something better will happen. So let's do this. So starting from here, we'll do more Cauchy-Schwarz. So what I will do is I will start with this and I will fix the sum over x and then I'll Cauchy-Schwarz to double the h and k variables. So every time you Cauchy-Schwarz, you're basically duplicating variables that were not fixed in the sum. So let's do some more Cauchy-Schwarz. I'm going to stop paying attention to the powers of delta. So now instead of h and k, we have h1, h2, k1, k2, and we have f0 of x plus 2, h1, k1 plus h2, k2. Sorry, f of x, f0 of x plus 2, h1, k1 plus h2, k2. And the point is that this expression h1, k1 plus h2, k2 is better anti-concentrated or better equidistributed than hk. And the reason we had trouble with hk is that a number with a lot of prime factors will be expressible more times as hk. But something like this equidistributes a little bit better.
Can you write what that is?
This?
Yeah.
It's gotten smaller and smaller.
So I'm just duplicating the variables.
It's h, can you just,
h1, k1 plus h2, k2.
I mean, I should really, my eyesight.
Small from here.
Yeah, I can usually see.
Okay. I'll write the next step bigger. So this is still not good enough. It's still not anti-concentrated enough, but we'll do Cauchy-Schwarz again.
H1.
And we'll duplicate the variables again. And so what are we going to get? So now we have 4 copies of all the h's and k's. F0 of x, f0 bar of x plus 2 times h1, k1, all the way up to h4, k4. And it turns out that this expression, where you have 4 terms, is sufficiently anti-concentrated by a sort of elementary argument with some GCDs, and that's about it. And so if we do these couple of extra Cauchy-Schwarzes, we can then carry out this strategy from the board above. And this is an example of concatenation, because we started with an average of box norms, and then we eventually reached just a single box norm.
Is there a formal definition?
No, it's a family of techniques. Okay, so this is a lot of calculations, but I hope the general scheme is starting to become clear. So we apply Cauchy-Schwarz, and then we apply Cauchy-Schwarz more. That's the name of the game in this area.
I mean, do you know how to, if I were looking at Liebman and Bergelsen,
So they do the pet induction, but not the concatenation. Everything they do is infinitary, so this doesn't.
everything is vowel differencing canonical.
Yeah.
And not this part.
Well, I mean, this should be Vanderkorp, it's all the same.
Is the reason that at 4 it's good enough somehow philosophically related to sum of 3 cubes versus sum of 4 cubes, 4 squares rather?
I have no idea. I can tell you concretely, 2 terms is not enough, 3 terms is enough. But we double at each stage, so we go directly to 4. And the reason 2 is not enough is if you just are looking at H1K1 equals H2K2 and you can factor. But once you have 3 terms, you don't have the factorization. Okay, so I want to sketch how this works more generally. So if you give me any multidimensional polynomial configuration, I can play the same game. And the first step is we use this pet induction and we do Cauchy-Schwarz a billion times. And we get largeness of some average of box norms, kind of like what we had before. And then the concatenation step is where we want to obtain a single box norm instead of this funny average. And to do this, we construct a system of multilinear expressions that are jointly nearly equidistributed. Here we have a single expression, which was this HK, and we replace it by this H1K1 plus ... H4K4. But in general, we have to do something a little bit fancier. And just to give you a feel for how much worse it is, if you put in corners with side length z² plus z, the pet induction step gives you a degree 7 box norm, whose boxes are in these directions. So the first thing to note is that when we start doing this pet to isolate one argument, the situation gets worse before it gets better, and that's why we end up with 7 terms instead of just the initial 3 that we started with. And the other thing to note is that the horizontal and vertical directions are kind of coupled. So you see that H3 appears here in the first coordinate, one of the H's should appear in both coordinates. Okay, but you see these, here I have my 2H2 plus 2H3, and then here I have 2H2 alone. So there are a lot of things I need to simultaneously equidistribute. And this is basically what we do. So I actually didn't want to go into the details of how we do this, but basically we iterate this Cauchy-Schwarz idea and we construct larger and larger systems that sort of have pieces that individually look like that. Okay, and then some remarks. This pet induction and concatenation in particular has been useful in other places. So it's useful for this recent result of Green and Sawhney on counting pairs of primes PQ such that P² plus 4Q² is also prime. So they're using this to handle their type 2 sums. And there's also been some recent applications in ergodic theory. So Borys and some of his friends have done some work on ergodic averages along Hardy sequences. And Marius and Sarah and 2 other people have used our concatenation result in some work on pointwise convergence of ergodic averages. So again, it's the kind of thing that was more or less known in any particular situation someone needed, but it's convenient to have it written out in full generality. Okay, so that's about all I wanted to say about pet and concatenation. But if you just do you take this example, it's the very simplest example. If you look at a couple more examples that are slightly more complicated, you get a feel for the type of Cauchy-Schwarz sequence of applications that will replace your funny looking polynomials with things that are better equidistributed. Okay, and then I want to conclude just by saying a few words about the degree lowering step. This will not be nearly as thorough because I'm condensing 60 pages into one slide, but I want to tell you some of the tools. So by the dual difference interchange, which is a standard trick, it suffices to show that U2 cross U1 control implies U1 cross U1 control. So you assume that we have the conclusion of our theorem with U2 cross U1 instead of U1 cross U1. And we want to use this to deduce that the conclusion of the theorem holds with U1 cross U1.
What's U1, U2, U1? I don't understand.
So this is a box norm where you're taking two derivatives horizontally and one derivative vertically. And this is a box norm where you're taking one derivative horizontally and one derivative vertically. So we started out taking t derivatives in each direction, and we're reducing this one by one. So suppose that we already know that the theorem holds for U2 cross U1. Okay, well, if our lambda p tilde is big, then we know that we have largeness of the U1 cross U1 norm of the first argument. And then, just like we had an inverse theorem for the U1 cross U1 norm, we know that if a function has big U2 cross U1 norm, then it has a certain form. And you can substitute this in using a trick called stashing. So this was previously our argument F0, and in it we've put in a U2 cross U1 obstruction. And we get that this expression is really big. And what's the goal from here? The goal is to find some phase alpha such that this function a of y is very close to alpha for many choices of the y's. And this will let us replace this function here, which is a U2 cross U1 obstruction, with just the function e of alpha x, which is an obstruction of lower degree. And the way you can see this is that to make this e of a of yx be uniformly 1, you have to take two discrete derivatives. But for e of alpha x, you can just take one discrete derivative, namely in the y direction. So if we can do this, then we'll be done. We will have lowered the degree, and there's still some work that has to be done to transfer this degree lowering back to our original setting, but this is where the real difficulty lies. And it turns out that after a lot more manipulations, including another whole run through of pet induction, you can show that if this is big, then this expression down here is big.
The phase was because you allowed some, when you get to more complicated things, you need null sequences. It seems like.
Yeah, so there's no nil sequence here.
Yeah, right.
There is a nil sequence here.
I'm trying to understand where that. So
Yeah.
we could,
So you start with this guy. You do a bunch of manipulations, and eventually you reduce this to a 2-point configuration.
and it's
And then you do pet induction again,
Right.
and you get largeness of something that basically looks like this with respect to some u to the t norm for large t.
you do the high T's where you would.
Yes, because you basically have to Cauchy-Schwarz a billion more times to kill these p tilde of
So
z's.
that's where the no.
So that's where it comes from. So you end up getting an expression that looks like this. So phi is our nil sequence, and we have an expression where e of a of y p tilde of z is correlating with our nil sequence evaluated at something. So you want to understand when this thing can be large, and this is where we use the heavy machinery. And we use James's new results on the inverse theorem and this quantitative equidistribution stuff. And the idea is that you use an iterative process to replace this nil sequence by progressively simpler functions. And by the time you've replaced it with the function 1, we're left with just this exponential sum. And then Weil gives us that that A has to be major arc, and then you pigeonhole in the major arcs. So this is sort of a microcosm of the proof as a whole. And I should mention that this nil sequence degree lowering thing is very delicate, and this is another place where we use the simple integer root. And I can say maybe another word about this because people were asking. So I've said for a while you could ignore the W trick, but here it's actually an issue because all of the things in the inverse theorem and the equidistribution for nil sequences depends a lot on the particular coefficients of your polynomial. And the problem with W tricking is that the coefficients become very big. They grow with W. It turns out that you can use some GCD Euclidean algorithm type tricks, which basically appeared in Sarah Offerham and Tom's paper, to get around this when you have a simple integer root. But without it, we don't know how to do it. Okay, so that was all I wanted to say, and thank you for listening.
Questions?
Metab, when he was using this, was using your techniques, or was he quoting? Is your paper such that there's statements that you can use directly, or do you really have to study the back? I can't remember what he was saying.
Yeah, so
He just said,
yes, so if you have any one of these multidimensional polynomial configurations, you can just quote our paper. He used
theorems there with bounds that are sufficient.
yes, the bounds are basically as good as you can ever hope for. You have polynomial losses in delta, but this is inevitable. He is able to quote an intermediate result. So I didn't say how you, in general, produce these systems of multilinear equations by sequences of Cauchy-Schwarz, and we do this sort of in 2 stages, and he quotes the output of the first stage. which, as he complains, is buried deep in section 7 of the paper, or section 8.
And was the reason, I'm just trying to remember that day, because I don't know what this was.
So the problem is that they don't have boxes. They have something that looks like a box norm. Sorry, they do have boxes. The problem is that their boxes are not intervals. So they have something that looks like a box norm, but the boxes have these like images of the squares, basically. And we're doing everything where the boxes are intervals.
So you can't work.
So you can't quote it for everything. But you can quote it for these polynomial configurations. Yeah, so really what I should say is we analyze very closely the kinds of polynomials that can come out of pet induction. And it turns out that these are always multilinear. And so we handle this quantitative concatenation for the setting of multilinear polynomials, but they have a square.
More questions? Say no again.